Right, so now we're going to talk about this tool that you'll use quite a bit in all the equilibrium problems you'll see, and this is called the ICE table. And it's nothing but a tool. It's just a way to organize information in equilibrium problems, makes it really easy for us to see what's being asked, what's given, and how to do the calculation. And the reason it's called the ICE table is because we split a reaction into 3 time points. The first one is what is there at the beginning, so that's called initial. And then the second is what's going on during the reaction. What has changed? Is reactant being consumed? Or is product being consumed? So we have to indicate that. And then lastly, what's there at the end, which is the equilibrium. So that's the essence of the ICE table. It's just a way to organize information. The best way to learn this is really to do some problems. So we're going to look at a couple of examples here, highlight some of the ideas in using the ICE table to solve equilibrium problem. Let's look at that first problem. It says a mixture of half a mole of hydrogen and half a mole of iodine was placed in a 1 liter stainless steel flask at a certain temperature, gives us the equilibrium constant, which is 54.3 for the reaction. And then it says calculate the concentration of all species at equilibrium. Okay, so the first thing is just write the reaction out, which I've done here on the right side. And I've put in the two numbers there, half and half. But notice that since K calculations is done using molarity, what you want to do is make sure that you already convert those numbers into molarity. So these half and half that I put there, they're both molarity numbers. Now, as it happens, it's the same as the number of moles because in the question, we have half a mole, but we have 1 liter of a container volume. So it's when you divide the half by 1, you just get half back, okay? Now, it only tells us that those two species are present. It doesn't say that the HI is present, so we can assume that that one is 0 at the beginning. Okay, so there's no product, which makes the reaction easy to understand in terms of its direction. We can say that it's going to go towards the product side, right? It's product favored in this case, or it's shifting to the right side because there's no product to begin with. How do we indicate that on the change? So that's our second row in the ICE table. We have to say that there is going to be a subtraction, so minus and minus on the reactant side and a plus on the product side. And then what quantity should we put in there? Well, we don't really know how much will change, right? There's some quantity of reactant that will be consumed and some quantities of product will be formed. What we can say is that let's represent that as X. We don't really know what it is. Now, based on stoichiometry, if I'm losing X number of H2, I have to lose the same number for I2, right? And that also means, because of stoichiometry, I have to gain double the quantity of HI. Again, because the coefficient for HI is 2, coefficient for H2 and I2 are both 1. The equilibrium is the easiest to fill out because it's just sum. You're just adding. If I put like a little plus sign there, you're just adding what you see in the first two rows. So half minus X, half minus X, and then this is 0 plus 2X, so it's just 2X. What are they asking us? They're asking us for the value of these concentrations. They want to know concentration of equilibrium, so that means we have to solve for X in order to figure out that number. So what we're going to do is we're going to go to the K expression, in this case just HI squared over H2 I2, and that if we plug in what we see at equilibrium, it's going to be 2x in parentheses squared divided by half minus x times half minus x. Okay, and this whole thing should equal 54.3. You can see that this is just equal to half minus x squared. We can write it this way now. One of the most common techniques that people can use here is to do square root of both sides. So you get this on the left side and 7.36885 on the right side. Again, I don't want to do much rounding here. Just try to write maybe about 6-7 digits of numbers so you don't get rounding errors later on. I can then solve for X once I have, right? So, and if I do that, I should get X equals 0.393 molar. Remember that X here represents concentration. Now, X is not what we're looking for. It is a key to solving our problem. What we're looking for is actually the equilibrium concentration. So let's calculate those. So the equilibrium concentration of H2 happens to be the same as I2, and they're both 0.5 minus X. So now that we know what X is, we just substitute that in the expression, and what we get is 0.107 molar for both H2 and I2. For HI at equilibrium, put this EQ subscript to indicate that that's equilibrium concentration. In the ICE table, concentration of HI at equilibrium is 2x, so then it would just be 0.787 molar. Hopefully that works out pretty easily for you in terms of using the ICE table. Now let's look at a second problem where we can use the ICE table. Another equilibrium problem right here. Same reaction, H2, I2 goes to HI, same K therefore. But the difference is that the initial concentration are given for all three species. So three numbers here. And they're asking for the same question, which is what is the concentration of these species at equilibrium? Okay, so you might think, well, should be pretty easy, right? It's a slight tweak to the problem, add all three concentrations instead of only having two of them. Turns out it becomes significantly more difficult. You need another couple of steps to kind of figure this out, okay? So I'm writing the reaction again right here on the right, and now I have those three numbers at the start. The first question you should think about, earlier when we had this reaction, we just say since we have no product, it should go and make product. Easy enough. But now we can't say that because we have product. So which way does the reaction go? We learned previously that there's a way to tell which way the direction goes, and that is by comparing Q to K. So that's what I'm going to do right now. I'm going to calculate my Q, which is the same expression as the K, except that you're using these initial concentration, which is these three numbers right here. So when I plug those numbers into that Q expression, I get 19.45. 19.45 is less than the K because remember the K value is 54.3. So we can conclude because Q is less than K, the reaction is going to make some more product. Once we know that, then now we can go back to our ICE table and then we can write plus on the product side and minus on the reactant side. Happens to be the same as the previous problem in terms of direction, but it's not always going to be that way. You're going to see situations where it's going to be pluses on the reactant side and minuses on the product side. Once we have it, then we have our final concentration expression, which is 0.00623, 0.00414, and 0.0224 plus 2x. Now, if you work out the math here, it gets a little harder than the previous one, okay? So the K expression is going to be 0.0224 plus 2x squared over 0.00623 minus x, 0.00414 minus x, and then that all equal to 54.3. Not as easy as the previous one because you can't just take square roots of both sides because the denominator has different expressions. So this means you're going to have to do your cross multiplication. So I'm just going to write down what math steps you need to do. So you're going to cross multiply and then you're going to write a quadratic equation, right? Which should show you something in the form of ax squared plus bx plus c equals 0. Okay, then at that point you can then use the quadratic formula to solve for x. Now usually one of the x's is reasonable and the other one isn't. And it could be because one of the x would be a negative number, and remember x represents concentration, so it doesn't make sense to have a negative concentration. Or sometimes the x value will be bigger than the starting concentration. So you might get an x that's like bigger than this number, for example. Then you say, well, how can I lose more than I start with? So that also wouldn't make sense. So whenever you see situations like that, you know one of those x's can be ignored. So then there's only one correct answer and you choose that answer as your x and you plug it back into the expression to get your equilibrium concentration. I'm going to leave it up to you to solve that since you do want to practice with the quadratic formula. Just keep in mind that it's going to be minus b plus minus b squared minus 4ac over 2a. Okay? Once you finish the quadratic formula calculations, double check your answer. It should be the numbers that are listed there for that problem.